Alright, previously we discussed about what are the factors that can affect the resistance of a wire. So among the factors are the length, the cross-sectional area of the wire, and also the resistivity of the wire. And we also discussed the resistivity for conductor, non-conductor, semiconductor, and also for superconductor. Alright, so here we want to look at how is it that we can use the relationship between the factor that affect resistance to solve problem. Alright, so the first example, the resistivity of constant is 49 times 10 power by negative 8 ohm meter. Calculate the resistance of a constant wire with a length of 50 centimeter and a diameter of 0.6 millimeter. Alright, so the relationship, the equation that we get from the relationship is resistance equal the resistivity times the length over the cross-sectional area. Alright, so we can calculate the resistance by take the resistivity of the constant 49 times 10 power by negative 8 and then times the length. The length given is 50 centimeter. We must change it into meter. So 50 centimeter is 0.5 meter. And then divide by diameter is given is diameter 0.6 millimeter. But this is cross-sectional area. That means we must calculate the cross-sectional area from the diameter. Okay, so from the diameter we can see that the radius is 0.3 millimeter. Okay, so to calculate the cross-sectional area we use pi r square. So r is the radius. Radius is 0.3 millimeter, must change into meter. So 0.3 times 10 power by negative 3. And then pi r square, right? Okay, so this must be square. Alright, so calculate how much is the resistance. Okay, so you get 0.8665 ohm. Alright, continue with example number 2. Azwan is an electrical wiring contractor in Taman Kota Putri. He found that a coil of pure copper wire with a length of 500 meter and radius of 0.5 millimeter has a resistance of 10.8 ohm. What is the resistivity of copper? So R equals resistivity times length over the cross-sectional area. So the resistance is 10.8 ohm. Resistivity is the one that we are looking for. The length is 500 meter. And then the cross-sectional area can calculate from the radius. Pi r 0.5 times 10 power by negative 3 square. Okay, like that. Pi r square. So the resistivity should be, okay, you should get 1.6965 times 10 power by negative 8 ohm meter. Okay, the unit for resistivity is ohm meter. Okay, next we want to discuss a little bit of application of resistivity of conductor in daily life. Okay, so in different application we choose material with different resistivity. So for example, for heating element, if you want to use the substance as a heating element. What is a heating element? Heating element is a substance that can produce heat when we pass electric current through that substance. Okay? When electric current flow through it, then it will be able to produce heat. So why is it that it can produce heat? The main reason is because it has higher resistance. When the substance have higher resistance, that means the charge that want to pass through that substance, it will need to do more work to overcome the resistance. So if we have higher resistance, then it will be able to produce more heat lah. Because when the charge do work to overcome the resistance, the electrical energy will be converted into heat energy. Okay? And that means the substance will become hot lah. Okay, the temperature will increase. Okay, so the best so far lah. Okay, the best material for heating element is nichrome. Okay, nichrome. So one of the reason is because nichrome have high resistivity, and then nichrome also have high melting point, which is very important right now if you want to use the material as heating element. If the melting point is not high, then it will melt, right or not? It will melt and then it will damage, it will break. Okay, so of course you need a material that have not only high resistivity but also high melting point. Okay, understand? So where we can use this, use in electric kettle, heating plate, electric iron, and so on. So whatever electrical appliance that can produce heat. Alright. So you look at this structure, you look at this heating element. You see it's shaped like a coil, right or not? It's shaped like a coil. So the reason why it's shaped like a coil is to increase the length. Understand? Increase the length. So when the length increase, that means the total resistance will increase. So not only it can make the total resistance higher, but it will also increase the surface area. Surface area that come into contact with water, for example. Let's say you use this in your electric kettle. So if it is longer, that means the total surface area will be greater and more heat can be transferred into the water at the same time. Okay, it's very important to say that more heat go into water at the same time. You cannot just say more heat go into water because if it is short but you on for longer time, also you can get a lot of heat transfer into water. But if it is longer, more heat can go into water together at the same time go into the water. Okay, get the idea? Okay, this is very important. Okay, next, filament bulb. Okay, the filament bulb use tungsten filament. Okay, filament bulb is made from tungsten wire. So we call it filament because the tungsten wire that we use inside the filament bulb is extremely thin. Okay, the cross-sectional area is extremely small and it is also rolled. What does it mean by it's rolled? It means like this, it's coiled up. Understand or not? Okay, the tungsten filament is not only thin but it is also rolled. These two characteristics can increase the total resistance. Why? When the cross-sectional area is small, then the resistance can increase, right or not? Okay? When the tungsten wire is very thin, cross-sectional area will be small, the resistance will be higher. When it is rolled, or you can say that it's coil, okay, coil, then the length can be increased or not. Greater length, total resistance also higher. Get the idea? Okay, So these two characteristics increase resistance. When resistance is higher, then more of the energy that is carried by the charge will go to the filament. Okay, so the filament can release more energy lah. And the energy will be released in the form of heat and light. Okay, I repeat, when the charge passes through the tungsten filament, it will need to do work to overcome the resistance in the tungsten filament. So the work done will transfer energy into the tungsten filament and make the tungsten filament become extremely hot. It is so hot that it releases light energy. It glows. Okay, glow and produce light. Get the idea? Okay, So when you coil the wire or coil the tungsten filament, also have the same effect like increasing the surface area. That means if it's longer, then that means more light can be released at the same time. Okay, more light energy can be released at the same time. Alright. So the reason why we choose tungsten filament is because it has high resistivity, it has high melting point, so it can resist high temperature lah. It do not melt and break easily. But like what I discussed previously, actually tungsten filament, if it is not enclosed inside the bulb, inside the glass covering, if it is outside, you on for some time, it will just melt and break lah. That means the high melting point help a little bit, but the main reason why the tungsten filament can continuously release light without breaking, without melting, is because of the high pressure inside the bulb, inside the glass casing. Inside the glass casing you have inert gases. So the inert gases exert high pressure onto the filament. So it makes the filament the boiling point, actually it makes the boiling point become higher. Melting point and boiling point become higher. Okay? So you can on the bulb without it getting damaged very quickly lah. Okay, next is electrical wiring at home. Okay, you see just now the two application is the application for higher resistivity. That means if when we want to produce heat, we want to produce light, we want to use material with higher resistivity. But for electrical transmission, for wiring, for electrical wiring, the purpose of wiring is to transfer electrical energy, right? You want to transfer electrical energy. So if you want to transfer the electrical energy, you want the resistivity, or you want the resistance of the wire to be low. So if you want so how is it that you can make the resistance to be low? One of the method is you choose the material with low resistivity. Okay? You choose material with low resistivity. So for example, copper or aluminium, they will have smaller resistivity. Okay? Smaller resistivity. And copper and aluminium also have high melting point also lah. Why is it that we also need high melting point? Because when we use the electrical appliance for long period of time, the connecting wire or the wire, the wiring will also become hot also. Okay, get the idea? Because even though the resistivity is very small, but still have resistance. Okay, still have resistance. So when the charge want to pass through the wire, it will also need to do work to overcome the resistance inside the wire. So that work done by the charge transfer energy into the wire and make the temperature of the wire increase. Okay, understand? Alright. When we discuss about resistance, usually we will think that, oh, resistance is no good. But depend on the application, resistance can be resistivity that is high can be very useful. Okay, understand? But of course, in the context when you want to apply it to transmit electrical energy, then the high resistivity, it will cause a wastage of electrical energy. So for example, when you are using, when you are using your phone, when you are watching television, when you are using your laptop, your computer and so on, after you use for long period of time, it will also become hot, right now. Your phone become hot, your TV become hot, your computer become hot, your laptop become hot. The reason is because there are resistance in the wiring in all of these electrical appliance. Your handphone inside the electric circuit have resistance, although very small, but it still have resistance. The electrical circuit in the television also have resistance. So if after you watch for a very long time, the charge that flow through will slowly transmit, will slowly transfer heat energy into the circuit, okay, to overcome the resistance. So it will, all those electrical energy will change into heat energy. So in this context, it is resistance or high resistivity is something that is no good okay, because it causes electrical appliance to heat up and waste, not only waste electrical energy, but the constant heating up and cooling down of electrical appliance can make the electrical appliance break down faster. Understand? You understand why, right? Because the material, you heat up, cool, heat, cool, heat, cool, heat, cool, then very quickly the material will break down. Okay, understand? That is why there is there is a bulb, the world longest lasting bulb, already on for more than 100 years. Already on more than 100 years. So actually one of the reasons why the bulb can on continuously for more than 100 years is because it has never been turned off, understand? Just continuously on only, never turn off, understand? Okay, so can on more than 100 years. But right now I don't know whether the bulb is still functioning or not, I don't know The bulb is a bulb in the US, in the fire station. Okay, you got see the video before somewhere. Okay, there's a documentary somewhere out there okay, maybe we watch the same documentary All right, so that is the story Any question? Okay, before we go on, we want to go through these few graphs that show the changes in resistivity due to temperature. Okay, previously we got discussed that temperature can make the resistivity change. Okay, but the effect of temperature on resistivity is different for different type of material. So first we look at metal conductor. If it's conductor, higher temperature, the resistivity will become higher. Okay, higher temperature, higher resistivity. Okay, this is for conductor. However, for semiconductor, it is the opposite. When the temperature is high, the resistivity go down. You see or not? So that means for semiconductor, when the temperature increase, actually the resistance of the conductor decrease. Okay? The resistance become lower and lower as the temperature increase. This is for semiconductor. Okay, and then after that we have this one we have not superconductor metal. We want to compare the normal conductor and the superconductor. You see, superconductor, it will only become a superconductor when the temperature reach a certain critical temperature. Okay, when the temperature reach a certain critical temperature, then only the material can turn into superconductor. But of course, not every material can become superconductor, only certain material. Okay, but the critical temperature is extremely low. That means very cool, like negative 200 something degrees Celsius. Negative 200 something degrees Celsius. Some even almost zero Kelvin. 0 Kelvin. That means almost reach absolute zero. Okay, almost reach the absolute zero. For your information, in nature, in our universe, even the coldest part of space, the temperature is about 2 point something degree Kelvin. But in order for certain material to become superconductor, you need to lower the temperature until lower than the coldest part in the universe. Okay? So that means it's very difficult to have a superconductor. Okay, that is why we don't have everyday object, that is everyday electrical appliance that is made from superconductor. So usually superconductor is used in very large machine with cooling function. Okay, with a very strong cooling function. So for example, in MRI. Okay, magnetic resonance imaging. So in this machine, MRI, magnetic resonance imaging, it needs to produce a very strong electromagnet. Okay, this magnet is electromagnet. So last time in lower form science, you got learn how to produce electromagnet, right? Basically, as long as you have electric current, then the electric current will be able to produce magnetic field. Okay? So, if you want a very strong electromagnet, that means the current must be very high. The electric current must be extremely high. Then only you can produce a very strong electromagnet. But, if the current is very high, then a normal conductor will just heat up and melt and break down, understand? Because when the current is too high, the temperature, the conductor will become very hot. Okay, and then it will melt and it will get damaged. So, in order to produce a very high current, they need to use superconductor. So, they cool down the superconductor until the critical temperature, then the resistivity of the superconductor becomes zero. So the resistance becomes zero. So not only superconductor can produce very high current, but it can also save energy, save electrical energy. Why? Because when it becomes superconductor, the resistance is zero. If the resistance is 0, that means the charge no need to do work to overcome any resistance. No work done. So that means after you make the charge flow, when the charge start to flow in the superconductor, the charge will never slow down. It will never slow down. It will never lose energy. Understand? So it can continue to flow and flow and flow and flow and flow. Never going to stop. Understand? So you will be able to produce a permanent, like a permanent magnet like that lah. Okay, the charge continue to move, continue to flow. You continuously have electric current, so you continuously have a very strong electromagnet. Okay, get the idea? Okay, so this is a very useful material lah. Okay, superconductor. So in another place where you use superconductor is maglev train, magnetic levitated train. Okay, that you can go online and you look about this train lah. Okay, maglev. Okay, maglev, magnetically levitated train. That means the train that has no wheel. Okay, it use the magnetic polarity to levitate. That means it float on top of the train tracks. Okay, the maglev train, it float on top of the train tracks using the polarity of the magnet, so it don't need to use any wheel. Okay, so how is it can maintain continuously levitate, continue to levitate is by using superconductor. Once it charge up the superconductor to have current to flow, then it can turn off the electricity, can turn off the power supply, and the superconductor will continuously have current. Okay, continuously have current. So it will permanently produce electromagnet lah. But of course, you must maintain the temperature at the critical temperature. Once the temperature is higher than critical temperature, the resistivity start to increase. So the material will no longer be superconductor. And then the charge will need to do work to overcome the resistance. And then the charge will lose energy lah. Once there is no more energy in the charge, then the charge will stop flowing. Then there will be no more electromagnet. Okay, get the idea? Okay. Okay, we continue with electromotive force and internal resistance. Okay, so the short form of electromotive force is EMF, E dot M dot F. So when you answer essay question or structure question, you do not have to write the whole word electromotive force. You can just write E dot M dot F. I repeat, E dot M dot F. If you write EMF, wrong. It must be E dot M dot F. Must have the dot. Understand? No dot, wrong. Okay? No problem. After the F, you want to add many dots also can. No problem. But if you write E dot dot M dot dot F, then wrong lah. Okay? For your information lah. Okay? Must have E dot M dot F. Okay? So what is electromotive force? Okay, previously we got discussed a little bit what is electromotive force. Electromotive force or EMF, the symbol is epsilon. This is not a capital E, not capital E, it's an epsilon. Okay, so is the energy transfer or work done by an electrical source to move 1 coulomb of charge in a complete circuit. So we can calculate the electromotive force. Okay, the symbol electromotive force equals to this E represent the electrical energy or the work done lah, okay, work done. So this you can write in two ways. You can write W over Q also can. You want to write E over Q also can. Okay, no problem. Okay, so this is electrical energy. Or it can also, or the energy transfer lah, or work done. Okay, same thing. Okay, so this one is the every coulomb of charge. Okay, charge. Alright. So basically, what it means is like this. What is electromotive force? Is like this. You see, this is a power source, right? Not a battery. So this dry cell, the electromotive force of the dry cell is printed. Okay, it's labeled on the dry cell. So for example, this one is 1.5 volt. So 1.5 volt means 1.5 joule per coulomb. So what is the meaning of EMF of a dry cell equal to 1.5 volt? Okay, so if question asks like this, if question asks what is the meaning of EMF 1.5 volt, then your answer is EMF of 1.5 volt means the power source is able to do the work of 1.5 joule to drive every coulomb of charge around a complete circuit. Okay, electromotive force or EMF of 1.5 volt means the power source is able to do the work of 1.5 joule to drive every coulomb of charge around a complete circuit. Basically, it means that the power source can provide every 1 coulomb of charge the energy of 1.5 joule. Okay, the electrical energy of 1.5 joule, that is what it means. So if the label or the EMF of the power source is 12 volt, for example, then it means that the power source can supply 12 joule of energy to every coulomb of charge that come out. And then that 1 coulomb of charge will use that energy to go around the complete circuit. Okay, go around the complete circuit. Alright. Now, to compare between electromotive force and potential difference, okay, so you look at this. Okay, so let's look at this. We want to compare the electromotive force and potential difference because both the electromotive force and potential difference have the same unit, which is volt. Okay, electromotive force is also work done or energy per charge. Potential difference is also work done per charge. Okay, but potential difference is work done by every coulomb of charge to move from one point to another point in an electric circuit or in an electric field. Okay. So for example, let's look at this example. Alright, so when we turn on the circuit, let's look at this one, potential difference. Let's say that this dry cell have an EMF of 1.5 volt. Okay, let's say that this EMF, this dry cell have an EMF of 1.5 volt. Okay, so that means what? That means every 1 coulomb of charge that come out should have 1.5 joule of energy, right? So logically, from what we learn, This 1 coulomb of charge will go here, and then when want to overcome the resistance in this bulb, this 1 coulomb of charge will do the work of 1.5 joule, right? Not? So the bulb will get 1.5 joule of energy, right? So if like that, this voltmeter show the reading of the potential difference from here until here, right? Not? So this reading should show 1.5 volt also lah, because here to here every 1 coulomb do the work of 1.5 joule, so the potential difference here to here is 1.5 volt. So the reading will show 1.5 volt. This is what we learned in previous topic, right? Right. If you are listening lah, okay. If you are listening, then you know what I'm talking about lah. Okay. However, in reality, the reading will not show 1.5 volt. It will show a reading that is lower than 1.5 volt. The EMF of the dry cell is 1.5 volt, but the reading will show less than 1.5 volt. So for example, let's say it show, okay, let's say it show 1.4 volt. Let's say, for example. Why like that? Why only show 1.4 volt? Okay, before we think about the reason, let's analyze the situation. Okay, you see if the voltmeter show the reading of 1.4 volt, it means that every 1 coulomb of charge go from here to here, do the work of 1.4 joule, right? Right. So it means that this charge, that when want to overcome the resistance inside this bulb, it only do 1.4 joule of work only. So if the 1 coulomb of charge only do 1.4 joule of work, it will mean that the 1 coulomb of charge, when come out of the dry cell, only have 1.4 joule. It doesn't have 1.5 joule. Only have 1.4 joule. So why is it like that? Why is it that the label of the dry cell is 1.5 volt? If the label is 1.5 volt, it means that every 1 coulomb that come out should have 1.5 joule. But the reality is, when the charge come out of the dry cell, it will have less than 1.5 joule. What is the reason? The reason is because inside the dry cell itself have resistance. It is very logical. You just think that the dry cell itself, it have chemical inside, right? It have electrolyte, it have electrode, and it also have the casing, right? All made from conductor, or some is anyway lah. All the material that made up the dry cell, it definitely have resistance, right? That means when the charge want to come out of the dry cell, the charge must do work to overcome the resistance inside the dry cell first. Then only it can come out. Okay or not? So this resistance that is inside the dry cell, we call internal resistance. Okay, we call it internal resistance. Alright, so that means Okay, so I draw this one more time. I draw this circuit one more time down here. For your information, when you draw the circuit, okay, sometimes question will come out, ask you to draw the electrical circuit. When you draw, you must make sure that all of the lines, especially the connecting wire, it must be connected. It must touch. If it doesn't touch, for example, let's say like this, a small, it didn't touch, then it will be taken as the connection is incomplete. Okay? Really, you must draw that it touched. A little bit didn't touch, then it will take it that the circuit is incomplete. Incomplete, then that means the circuit cannot function. Understand? Okay? Please, you need to take this seriously. Don't think that, little bit only, no problem one. Yes, a little bit is a big problem. Okay, a little bit is already a big problem. Alright. Okay. Now, okay, so we look at this circle one more time. Okay, so this represents the electromotive force of the dry cell. Okay, and then I draw. Okay, here I draw this to represent the internal resistance. This is the electromotive force of the dry cell. This is the internal resistance of the dry cell. Okay? And okay, I draw like this. This shows that this everything is inside the dry cell. Okay, everything is inside. This is a dry cell, you see? Okay, this is a dry cell. This is the EMF of the dry cell. This is the internal resistance of the dry cell. So, if the label is 1.5 volt, that means every 1 coulomb of charge must have 1.5 joule. So the 1 coulomb of charge that come out from here carry 1.5 joule. But it need to overcome this resistance, overcome the internal resistance, then only can come out. So let's say that the work done to overcome the internal resistance is 0.1 joule for every 1 coulomb. So that means the charge that come out only have 1.4 joule. So this charge that only have 1.4 joule, when go through the bulb, it will only be able to do 1.4 joule of work for every 1 coulomb of charge. So the reading will show only 1.4 volt Get the idea? Okay or not? Okay, so this is the reason Okay, now what if you disconnect? What if we disconnect the circuit? What will happen? If we disconnect the circuit, what will happen is the charge will not flow here, right? Charge will not flow here. Okay, here no charge. So what happens? We take it that the charge, okay, here no charge. Okay, here no charge. So what happens is we take it that the charge have to pass through the voltmeter. Okay, have to pass through the voltmeter. We take it like that. However, the resistance of the voltmeter is infinitely high. Very, very high right now. The resistance of the voltmeter is very, very high. So when the resistance of the voltmeter is very, very high, what will happen to the charge is, the charge will do vast majority, almost all of the energy of the 1.5 joule that the charge has, almost all of them will go to the voltmeter. That means the internal resistance only get very, very small amount of energy. So let's say that the work done, at the voltmeter is 1.9999999999999 joule for every coulomb. When you take reading from the voltmeter, what is it that you see? 1.5, right? You will see that it is 1.5 volt. So it will mean that if you disconnect or you straight away connect the dry cell, let's say you have a dry cell, okay, you have a dry cell, you straight away connect the dry cell to the voltmeter, the reading of the voltmeter will show the electromotive force of the dry cell. Understand? So this is one method to measure the electromotive force of a dry cell. Understand? Okay, get the idea. Okay, any question until here? Can you understand? Any question? Okay. The problem, you see, the reason why is it that the energy will all go to the voltmeter is because the voltmeter have very high resistance. Compared to the internal resistance, the resistance of the internal resistance is extremely small. Right? But what if the internal resistance is quite big? What will happen? If the internal resistance is also quite big, what happens? That means the reading of the voltmeter will also not going to show the electromotive force. Because, for example, let's say that the internal resistance is very big, but still smaller than the voltmeter. So, for example, the charge that come out, it will do the work of 0.2 joule at the internal resistance, and then at the voltmeter here do the work of 1.3 joule. Right? It will become like that. Right? So that means the reading of the voltmeter will show 1.3 volt 1.3 volt is not the electromotive force of the power source. Right? Okay? This will become a problem when the internal resistance is quite big. So how? Let's say we have an unknown power source. We have this power source, there's no label. We don't know how much is the internal resistance. We don't know whether the internal resistance is big or small. So that means that even if we connect the voltmeter directly to the power source, we will not have absolute confidence. We are not confident that the reading will show the EMF. Right? Not sure. Because if the internal resistance is small, then okay it shows the EMF. But what if the internal resistance is big? Then the reading of the voltmeter is not the electromotive force. So if like that, what is it that we need to do? We have to find out by doing experiment. Okay? Okay, so what is it that I mean that if the internal resistance is high, then a significant amount of energy will go to the internal resistance. You have to look back at what we discussed previously in the previous topic. Okay, in the previous topic, we learned that, let's say we have two bulbs here. Let's say that this power source, this dry cell is 3 volt. Okay, if the dry cell is 3 volt, and if this resistance is 1 ohm, this is 2 ohm, what will be the potential difference in the first bulb and the second bulb? This one will be 1 volt, this one will be 2 volt. 1 volt means every 1 coulomb will do the work of 1 joule. 2 volt will means every 1 coulomb do the work of 2 joule to pass through the bulb or to overcome the resistance inside the bulb lah. So you see, higher resistance, the charge will need to do more work. Okay, will do more work. So you see, the power source is 3 volt, so that means every 1 coulomb that come out carry 3 joule. And this charge, it will allocate more work done, more energy to the higher resistance. Okay? Higher resistance will get more energy. So that means that if the resistance is low, then it will get less energy. Okay, now let's say that let's say now this one is, I change into internal resistance. This is actually the internal resistance inside the dry cell. So that means that if the resistance outside or the internal resistance is higher, then more energy, more work done will go towards the internal resistance. Same thing with if the external resistance is very high, then more energy will go towards the external resistance. So this is what I mean by, if the internal resistance is small and you straight away connect to the voltmeter, straight away connect to the dry cell, the reading will show EMF. Because the resistance of voltmeter is extremely high. So all of the work done, or almost all of the work done, will go to the voltmeter. So the reading of the voltmeter will show very, very near to the EMF that you cannot differentiate lah. Okay, you cannot even see the difference. So when you see, you just see that it is EMF. But if the internal resistance is high, that means the work done will split. That means there will be a significant amount of work done, energy go to the internal resistance to overcome the internal resistance. So that means the voltmeter will get less than the EMF. So the reading will show a reading that is less than the EMF. Okay, get the idea. So how to get the EMF? In this case, we need to carry out a certain experiment lah. So we will discuss this experiment in our next class. Okay.